Hello and welcome. Today we're going to be looking at question number 3 on the 2012 AP Chemistry exam. As always, we're going to be going through the entire pre-response questions so you get an idea of how to approach these questions and are ready to ace the AP Chem exam. If you like these videos or find them informative, please be sure to like and subscribe. And with that, let's get started on our question. Here it is. A sample of CH3CH2NH2 is placed in an insulated container where it decomposes into ethene and ammonia according to the reaction represented above. And we have a table of substance versus absolute entropy in S standard at 298 Kelvin. All right, and how are we going to use that? Well, let's see. So part A says, using the data in the table above, calculate the value in joules per mole Kelvin of the standard entropy change delta S for the reaction at 298 Kelvin. All right, let's do that. So we have for part A. So what is R? First, we're gonna write a reaction, right? So that's how we end up doing this, right? We're just going to write the reaction out, and the reaction is kind of simple, right? It's just CH, is that a 2? CH, 3 CH2, CH3, CH2, NH2, NH2. That decomposes to CH2, CH2, and NH3. So that's our reaction. Now, how do we get the standard entropy change from that? Well, we have the values for the absolute entropy of each of these. So we're just going to use the idea that we use, and when we're calculating these, which is just the sum of S for the products minus the sum of the absolute entropy of the reactants. So we're going to do that, and we're going to end up with 192.8 plus 219.3 minus 284.9, and we're going to get that this is equal to 127.2 joules per mole Kelvin, and that is our standard change in entropy of this reaction. Let's move on to the next part. All right, part B says, using the data in the table below, calculate the value in kilojoules per mole of the standard enthalpy change delta H after the reaction at 298 Kelvin. All right, so here we have for the bonds for C, for a single bond between two carbons, a double bond between two carbons, a CH single bond, a CN single bond, and an NH single bond. All right, so let's draw some of those structures out, and we can think about how we're going to go do this question. All right, so like this. So for the CH3, CH2, NH2, we have C, H, 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 connected to this one, which is an H and an H, connected here to an N, and then which is connected to two H's from there. So that's going to be the CH3, CH2, NH2. And then for the ethene and the ammonia, we have two C's with a double bond, and then H and H. And we have N, we have NH3 or ammonia. And I'm not gonna write out the electron pairs on the nitrogen because we really don't need it right now, right? What we do need to do right now is we need to think about how we're going to use this, right? How we use these bond enthalpies to find A delta H. Well, let's see. So when we break bonds, that releases energy. Now, when we break bonds, that takes in energy. Forming bonds releases energy. Right? So when we break bonds, you have to put in energy. When you're releasing bonds, you release energy. Or when you form the bonds, you release energy. Right? So what we're going to do is here, the enthalpy is going to be, well, the positive part is going to be of the positive part is going to be of what? The positive part is going to be when energy has to be put in, which is when you're breaking the bonds, which is going to be for the reactant, right? That's what you do in the reactant. You break the bond. And then you're going to subtract that by the negative part, which is when you are, when you're releasing energy, which is when you're forming the bonds, which is for the products. So here what's going to be the opposite. It's going to be the sum of reactants minus the sum of products, which is going to be, what? Well, let's see. So right here in this one, we have 1, 2, 3, 4, 5 CH bonds. We have one CC bond, and we have one CN bond, and two NH bonds. All right, that's what we have in this Lewis structure. All right, now let's go to this one. We have 4 CH bonds. We have a double bond in the carbons, and then we have 3 NH bonds. Alright, so how do we go about doing this now? Well, we have 5 CH bonds to start with, and now we have 4. So essentially, we can make a table of broke versus formed. So we broke a CH bond. Alright, then what? Well, we had a CC bond to begin with. Now we don't have a CC bond. We also broke a CC bond. What else? Well, we had a CN bond to start with, so that's another thing we broke. And then we had 2 NH bonds, but that's not something we broke since we ended up with 3 NH bonds. So let's look at formed now. So we formed a double C bond. We formed another NH bond. And that would be it. That is our entire table for the bond enthalpies. So now we just have to take the positives of CC and the NH bonds. It's positive because those are the ones that, or no, we're going to take the positive of the reactants minus the products, right? Since as we set up here, reactants minus the products, right? So we have the reactants as a CH 413. That was a horrible 413. A CC bond, single CC bond, which is 348 kilojoules per mole. A CN bond, which is 293. And then we're going to subtract that by double C bond, which is 614, and an NH bond, which is 391. And I get, taking my calculator, plugging all that in, right? 413 plus 348 plus 293 minus 614 minus 391 is going to be just the end. That's going to be just 49 kilojoules per mole. as our enthalpy. That's it. And we can move on to the next part. Alright. Now we're told, based on your answer to part B, predict whether the temperature of the contents of the insulated container will increase, decrease, or remain the same as the reaction proceeds. And we're asked to justify our prediction. So we're thinking about this based on the answer to part B, which is that the enthalpy is 49 kilojoules per mole, which means what? It means it's endothermic, right? So we know that it's endothermic right now. So we know that this reaction is endothermic, right? Now, how do we use that information? We're trying to predict whether the temperature of the contents will increase, decrease, or remain the same as the reaction proceeds. So what do we know as the reaction proceeds? Well, since the reaction is endothermic, right, we're basically sucking in heat from the system, the environment, sucking heat from the surroundings into the reaction. So the heat around is going to decrease, which means that the temperature is going to decrease. Right, so let's verbalize that. So I'm going to get a text box. Right. So we have since the change in enthalpy is positive, the change in enthalpy is positive, then we know that the reaction is endothermic and sucks heat out of the surroundings as the reaction proceeds. So the surroundings lose heat and therefore decrease in temperature as the reaction proceeds. And our answer is that the temperature is going to decrease. Let's keep going to the next part. Right, so I'm going to scroll down so we can see the rest of this. So let's see. An experiment is carried out to measure the rate of the reaction, which is first order. A 4.7 times 10 to the negative 3 mole sample of CH3CH2NH2 is placed in a previously evacuated 2-liter container at 773 Kelvin. After 20 minutes, the concentration of CH3CH2NH2 is found to be 3.6 times 10 to the negative 4 moles per liter. And we're asked to calculate the rate constant for the reaction at 773 Kelvin. Alright, let's think about this. Alright, let's think about how we go about doing this question. Alright, so one of the equations on the equation sheet is the one for a first order reaction, right? Because they told us it's first order, so we can use that. It's first order, so we know that we can use the equation, and that we can use the equation that the ln of the concentration of something of, let's just call it A here, A final, minus the natural log of the concentration of A initial is going to be equal to negative K times the time. Basically the time it takes to get from final to initial. So really, if we wanted to, we could write it as, instead of final initial, we could write it as simply this is T and this is 0. Now, how do we use that? How do we use this equation? Well, we know that we started at 4.7 times 10 to the negative 3, and we finished out at 3.6 times 10 to the negative 4. Alright, so we're just going to take that and plug it into the reaction. So we have the natural log of final, which is 3.6 times 10 to the negative 4, minus the natural log of 4.7 times 10 to the negative 3, divided by negative KT, so we're going to divide by the time, the negative 20 minutes, and that's going to give us K, our rate constant, since that's what we're trying to find. So we're going to figure that out, and we're going to get that natural log 3.6 times 10 to the negative 4 minus natural log of 4.7 times 10 to the negative 3 divided by negative 20 is going to make the rate constant equal to what? It seems like it should be 0.128. However, this is incorrect, right? And we need to think about why it's incorrect, right? This is why you need to understand how the equation works rather than just memorizing the equation, right? This is why you should really take some time to think about why all these like integrated rate laws or just the equations in general, why they work, instead of just relying on the equation sheet. These are two concentrations. These are concentrations. All right, we plugged in 4.7 times 10 to the negative 3. It says 4.7 times 10 to the negative 3 moles, right? That is not a concentration. That's a number of moles. So you have to divide that. You have to divide that by 2 liters. By 2 liters. And then we're going to divide by 20. And then let's try this again. All right. So we have divided by negative 20, and that is going to make the rate constant equal to 9.38 times 10 to the negative 2. And our units, well, this in the top, there's not going to be any units because it's just natural logarithms, get rid of the units. The bottom is in minutes. This is going to be in 1 over minute. And our answer is 9.38 times 10 to the negative 2 per, 1 per minute, or minute to the negative 1. And that is our rate constant. Let's keep going to the next part. Alright, the next part, part E, says calculate the initial rate in molarity per minute of the reaction at 773 Kelvin. Well, what do we have here? So we know that the rate law, right? We figured out that the rate law is K, the K that we just found, times the concentration of this A to the first power, since it's first order. So what we do here is we're just going to multiply the 9.38 times 10 to the negative 2. We're going to multiply that by our initial molarity, our initial concentration, which is the 4.7 times 10 to the negative 3 over 2. And that's going to be equal to, what is that going to equal? That's going to equal to, that makes our initial rate equal to 2.20 times 10 to the negative 4. Right? And that's going to be in molarity per, and that is our initial rate. Right. Let's keep going on to part F. And it is, if 1 over CH3CH2NH2 is plotted versus time for this reaction, would the plot result in a straight line or would it result in a curve? Explain your reasoning. Well, let's see. Make text box so we can kind of get our thoughts down. Well, since the reaction is first order, it follows the integrated rate law that we used above, right? Where the difference in the natural logarithms of the 2 points makes a linear graph, right? So this means essentially is that, so the graph will be a straight line, since it is first order, and the graph of a natural logarithm of a first order reaction versus time is going to be linear. Right, so for each of these orders, we have a separate graph that's linear. For 0, it's just the graph concentration versus time. For first order, it's natural logarithm versus time. For second order, it's the reciprocal over time, so 1 over the concentration over time. So that's going to be 1 over the, so this is going to be a natural logarithm, it's going to be linear. Is that what it says? No, it's not. Think again. Right, this is where you need to really look at the question. Because usually when they give you these kinds of questions, they'll give you the right version. But this is not the right version. It follows the integrated rate law where the difference in natural logarithms makes a linear graph. This is not a natural logarithm. It's going to be a curve. Since this is not a natural logarithm. This is the graph of a natural logarithm. Is the natural logarithm of the first order reaction versus time is going to be linear. This is the graph of the reciprocal versus time, which is only going to be linear for a second order reaction. Since this is first order, it will not be linear. And is instead a curve. Alright, so this is another place where you really have to think about what the question is asking for, and you really have to think deeply into what you're actually doing with the question. Don't just sit there and plug in equations. That's not what the point of this exam is. The point of the exam is for you to understand how these things work. And that's how, if you know that, you'll be able to fly through these questions to do them perfectly. That is it for this pre-response question. Be sure to tune next time when we continue looking at more of these AP Chemistry pre-response questions, and I'll see you next time.